The Milky Way Galaxy, our cosmic home, is a barred spiral galaxy that spans about 100,000 light-years in diameter and contains over 200 billion stars. It is a member of the local group of galaxies and is part of the Virgo supercluster. Our solar system is situated in one of the Milky Way's spiral arms, known as the Orion Arm or Orion Spur, about 27,000 light-years from the galactic center. The galactic center hosts a supermassive black hole named Sagittarius A*, which has a mass equivalent to about 4 million suns. The Milky Way structure is composed of several key components, including the galactic bulge, disk, and halo. The bulge, a dense region of stars, gas, and dust, is located at the core and is thought to house older stars. Surrounding the bulge is the galactic disk, which contains the spiral arms and most of the galaxy's star formation activity. The disk is rich in both young and old stars, as well as interstellar gas and dust. Beyond the disk lies the galactic halo, a spherical region containing globular clusters, dense groups of ancient stars, and dark matter, which makes up a significant portion of the galaxy's mass. The Milky Way is not a static structure. It rotates with stars and other objects orbiting the galactic center. This rotation gives rise to the differential rotation curve, observed as stars closer to the center orbit faster than those further out. Additionally, the Milky Way is moving through space, interacting with its neighbor galaxies, such as the Andromeda Galaxy, with which it is predicted to collide in about 4.5 billion years. Through the use of various observational technologies, such as optical telescopes and radio waves, astronomers have been able to map and study the Milky Way, gaining insights into its composition, formation, and evolution. Understanding our galaxy helps us comprehend the larger workings of the universe and our place within it, offering a profound perspective on the nature of existence. In the not-too-distant future, humanity had finally perfected intergalactic travel. The Andromeda Galaxy, a colossal spiral of stars and planets 2.5 million light-years away, became the first destination. The Starship Odyssey, equipped with advanced propulsion systems and a crew of brilliant scientists, set off on an ambitious exploration mission. Captain Emily Rivera led the diverse team, composed of astrophysicists, biologists, engineers, and an AI named Nova, designed to handle vast amounts of data and support decision-making. As they approached Andromeda, the sheer scale of it left everyone in awe. Stars shimmered like scattered diamonds against the black void, and planets of all sizes orbited their suns in magnificent cosmic ballets. Their primary objective was Exoplanet XC-276, rumored to have conditions suitable for life. Upon entering orbit, they launched probes to analyze the planet's atmosphere, oceans, and terrain. The data Nova process suggested a high likelihood of microbial life. Excitement surged through the crew as they prepared for a landing. Landing on XC-276 was challenging. The planet's surface was a rugged terrain of mountains, valleys, and sprawling oceans with vibrant coral reefs seen from above. Once on the ground, the team set up a base camp and started their experiments. Dr. Lee, an astrobiologist, led the charge in collecting soil and water samples. Initial results confirmed the presence of simple life forms, sparking debates about the possibility of more complex organisms. While exploring a nearby cave system, they discovered ancient fossilized remains, hinting at an advanced extinct species. As they delved deeper, they stumbled upon remnants of what appeared to be a civilization: tools, carvings, and structures. Nova's analysis suggested these were millions of years old. The discovery had profound implications for understanding life's potential in the universe. However, their excitement was tempered by signs of a past cataclysm. Evidence pointed to a massive asteroid impact, likely causing the extinction. This revelation served as a sobering reminder of the fragility of life. After months of exploration, Odyssey prepared for their return to Earth. They carried invaluable data and samples, forever altering humanity's understanding of the cosmos. The mission had been a tremendous success, but it also raised new questions about the fate of civilizations and the importance of safeguarding their own. Deep in the cosmos, where light itself takes millions to billions of years to traverse, lie some of the most mysterious galaxies ever studied by astronomers. These celestial phenomena intrigue scientists not just because of their visual splendor, but also due to the enigmatic processes occurring within and around them. Among these, three galaxies stand out: IC 1101, Hove's object, and the Sombrero Galaxy. IC 1101 is the largest known galaxy in the observable universe. Located over 1 billion light-years from Earth in the constellation Serpens, this supergiant elliptical galaxy stretches about 6 million light-years across, compared to our Milky Way's measly 100,000 light-year diameter. What makes IC 1101 so mysterious isn't just its size, but its composition and the extremely old stars populating it, suggesting an almost dormant stellar environment possibly rich in dark matter. Hove's object is another enigma that has puzzled astronomers since its discovery by Arthur Hogue in 1950. This galaxy exhibits a rare ring structure unlike the traditional spiral or elliptical shapes observed. Its center consists of a dense core of stars, surrounded by a perfect ring of young, hot blue stars, separated by a peculiar void of almost nothingness. Hogue's object challenges our understanding of galaxy formation, prompting numerous theories, none of which completely explain its unique structure. Lastly, the Sombrero Galaxy, or M104, is easily identified by its bright nucleus and the extensive dust lane encircling it, resembling a sombrero hat. Located about 31 million light-years away in the constellation Virgo, this galaxy's halo contains innumerable globular clusters, far more than the Milky Way. Its enigmatic glow and structure suggest some unusual processes at play, possibly involving a supermassive black hole at its core, fueling heightened curiosity and continuous observation. Each of these galaxies represents a puzzle piece in our broader understanding of the universe. They are studied not just for their individual peculiarities, but for the broader implications they hold for the formation, evolution, and fate of galaxies across the cosmos. With each new finding, astronomers are reminded of how much we have yet to discover in this ever-expanding cosmic odyssey. The future of space missions and galaxy exploration is poised to be marked by unprecedented advancements and scientific achievements. As technology evolves and international cooperation strengthens, humanity's ambition to unearth new celestial mysteries continues to grow. NASA's Artemis program aims to return humans to the moon by the mid-2020s, utilizing innovative spacecraft like the Orion capsule and the Space Launch System, SLS. This endeavor will serve as a stepping stone to more distant destinations, including Mars. Private enterprises like SpaceX and Blue Origin are also at the forefront of these efforts, with ambitious plans to colonize Mars and establish a lunar economy. SpaceX's Starship, a fully reusable spacecraft, is designed to transport large numbers of people and cargo, facilitating regular interplanetary travel. Blue Origin's Blue Moon lander will support lunar science, exploration, and commercial missions, contributing to a sustainable human presence on the moon. The European Space Agency, ESA, and the Russian Space Agency Roscosmos are collaborating on the ExoMars mission, aiming to detect signs of past life on Mars and better understand its environment. Meanwhile, the James Webb Space Telescope is set to launch, offering unprecedented views of the universe's earliest galaxies and potentially unlocking new knowledge about the origins of life. Furthermore, international efforts such as the Lunar Gateway, a space station intended to orbit the Moon, will provide vital support for exploratory missions and enable deeper space travel. In addition to governmental and private sector initiatives, academic institutions and smaller organizations are also playing significant roles. Universities are building CubeSats and conducting research to develop new technologies for sustainable space exploration. These collaborative efforts underscore the intersection of innovation, exploration, and scientific curiosity, driving forward the next era of space discovery. As we stand on the cusp of this new frontier, the potential for groundbreaking findings and transformative impacts on our understanding of the universe is immense. The coming decades promise to be an exciting period for space enthusiasts, scientists, and the general public alike, as we boldly go where no one has gone before. Dark matter is an elusive yet fundamental component of the universe, accounting for approximately 85% of its total mass. Unlike ordinary matter, dark matter does not interact with electromagnetic forces, meaning it does not emit, absorb, or reflect light, making it incredibly difficult to detect. Despite this, its existence is inferred through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. One of the most significant roles of dark matter is in the formation and evolution of galaxies. Dark matter provides the necessary gravitational framework for galaxies to form and stabilize. In the early universe, dark matter clumped together under its own gravity, creating deep potential wells. Ordinary matter, primarily hydrogen and helium, fell into these wells, ultimately cooling to form stars and galaxies. Without the presence of dark matter, the observed distribution of galaxies across the universe would be vastly different. Dark matter halos, which envelop galaxies, are critical for maintaining galactic stability. These halos provide the additional gravitational pull that keeps the rotational speeds of galaxies' outer regions consistent with observations. Without dark matter, the outer stars of galaxies would rotate much slower, defying the laws of Newtonian mechanics. Furthermore, the role of dark matter extends to galaxy clusters, the largest gravitationally bound structures in the universe. Within these clusters, dark matter acts as an unseen glue, binding galaxies together and affecting their motion and interaction. Observations of gravitational lensing, where light from distant objects is bent by massive foreground objects, provide compelling evidence of dark matter's presence in galaxy clusters. Despite the significant advancements in understanding the role of dark matter, its true nature remains one of the most profound mysteries in cosmology. Various candidates for dark matter particles, such as WIMPs, weakly interacting massive particles, and axions, have been proposed, but none have been detected directly. The search for these particles involves highly sensitive detectors placed deep underground to shield them from cosmic radiation. In conclusion, dark matter plays a vital role in the structure and behavior of galaxies and the universe at large. While it remains invisible and mysterious, its gravitational imprint is unmistakable, guiding the formation of galaxies and the dynamics of the cosmos. The quest to uncover the nature of dark matter continues to drive forward the boundaries of astrophysics and cosmology.